So we're going live on YouTube. So we're going live on YouTube. Morning, Suri.
Good morning. Good morning.
Morning, Vijay.
Morning. I'm sorry.
Right. Indulekha, I think we can start.
The clock might strike in between. That's why I waited a bit.
Means we should start a bit earlier.
Yeah. Please strike 11 times. So good morning, everybody, and welcome to our participants, speakers, and chairs. So today is the 5th day of the Resonance Lecture Series, organized in celebration of 25 years of publication of Resonance. We are extremely happy to have Professor Mukherjee as our first speaker. We have Professor Ambrish Shivaji as our chair. Professor Ambrish Shivaji, he's from IISER Mohali. He did his education, PhD in physics from the Institute of Physics, Bhubaneswar. After that, he was a postdoctoral research fellow at the Harish Chandra Research Institute in Allahabad. Again, postdoctoral research fellow at the National Institute for Nuclear Physics, Italy. Postdoctoral research fellow at the Catholic University of Louvain in Belgium. And he has been an assistant professor at IISER Mohali since 2018. He's a particle physicist. And his research interests include phenomenology of loop-induced processes in the standard model and beyond that, higher order quantum corrections, and model-independent approach to the study of new physics effects, mainly in the Higgs sector at colliders. So I'm happy to have Ambrish Shivaji here as chair, and I hand over to the chair of this session. Thank you.
Thank you, Professor Indulekha. So as Professor Indulekha mentioned, the first talk is by Professor Mukherjee. Let me introduce the speaker. Professor Mukherjee, currently a visiting professor at IIT Dhanbad, completed his PhD from the University of Calcutta in 1983. He gained postdoctoral research experience at IICS Kolkata and at Harvard University before joining the chemistry department at IIT Kanpur as a faculty in 1987. His research is specialized in the areas of coordination chemistry and bioorganic chemistry. He has published more than 150 research works in reputed international journals such as Inorganic Chemistry, Dalton Transactions, Chemical Communications, European Journal of Inorganic Chemistry, Inorganica Chemica Acta, Polyhedron, etc. Professor Mukherjee served as the head of the chemistry department at IIT Kanpur during 2010 to 2012, and then as the director of IISER Kolkata from 2012 to 2017. He is a recipient of the prestigious J.C. Bose Fellowship awarded by DST. He is a fellow of Indian Academy of Sciences, Bangalore, and Indian National Science Academy, New Delhi. Professor Mukherjee has also been a member of the Royal Society of Chemistry, United Kingdom, and the American Chemical Society, USA. Professor Mukherjee is going to talk about inorganic chemistry of biological process. With this, I request Professor Mukherjee to begin his lecture.
Thank you very much for the kind introduction. Now, so the point is, the title of my talk is Inorganic Chemistry of Biological Processes. The subject of inorganic chemistry is such that when it comes to biological processes, inorganic chemistry is way out. But actually, I will show you that a lot of metalloenzymes, without their action or functioning, we cannot survive. Anyway, let me start the journey first. So the way I have started doing, as it is a chemistry, basically, whether bio, inorganic or whatever, is chemistry. So chemistry goes all the way back to 1743, 1794. And all of us, we know about this man, the Lavoisier, who named both oxygen and hydrogen. And how do you define chemistry? Chemistry is a molecular science. More you know about molecules, more you know about chemistry. Because this is predominantly experimental science, but without theory, nothing can function. So I have sketched like this, the central chemistry, which is the backbone of the today. Chemistry is interfacing with biology, interfacing with material science, with physics, everywhere. And you see here, chemistry, the basic thing is the fundamentals of physical chemistry, then the long back organic chemistry, and in between with physical, we have the polymer chemistry, and inorganic also joined the wagon, and theoretical chemistry. Without that, you cannot justify certain reactions which take place. But these days means for the last maybe quarter of a century, 25 years or so, two things are very important: biological processes and material science. So chemistry of materials and the chemistry which what goes on in biological system takes a huge attention. So chemistry, what it does, it deals with bond breaking and bond making. That is the fundamental definition of chemistry. In the language of physical chemistry, it is basically reorganization of electronic charge density that take place during a chemical reaction. So say there is the A-B bond, C is coming. So electron charge density between A and B is changed now, and the new bond between A and C or B or C will take place. Now, what is bioinorganic chemistry? In one sentence, one can say role of metal ions in biology. And there are many, many elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, silicon, sulfur. They are all the non-transition metal elements. Okay, fundamental part, and that is also taken care of by the backbone of protein molecules. But what is the role of metal ions? Without metal ions, you cannot have a particular metalloprotein to assume a particular geometry. So the structural role is most important. And because of the presence of metal ions, one can carry electrons and carry oxygen. For our survival, we need oxygen. So we have in our lung, deoxy state, or not oxygenated state of hemoglobin called deoxyhemoglobin. And when we inhale oxygen, those deoxy state becomes oxygenated, and that oxyhemoglobin flows all over our body in the tissues where metabolism takes place. And for the metabolism, oxygen is released. And in the process, you generate carbon dioxide, which is insoluble in water. So there is an enzyme named carbonic anhydrase. What it does, simply solubilizes carbon dioxide like your cold drink. So carbon dioxide and water generates bicarbonate ion, which is water soluble. So basically you can see now two things. So oxygen carrying is important, and also electron carrying is important. During metabolism, certain things are getting oxidized, reduced, all kinds of redox phenomena. So electrons are getting transported. So transporting, that's why there are a lot of proteins which actually function in transporting electron, and some proteins will transport oxygen from one place to another. As for example, hemoglobin, myoglobin in vertebrates. In invertebrates, we have hemerythrin, hemocyanin. Hemocyanin is lobster, shrimp, is a copper containing. And hemerythrin is again iron containing without hemoglobin or the so-called porphyrin ring. Third role is carrying roles, catalytic roles in oxidation reduction reaction, redox reaction. The redox reactions are very, very important. As it is basically for undergraduate students, there are almost all reactions, there will be some, not all reactions are redox in nature, but when you predict a chemical reaction will occur or not thermodynamically, redox reaction, then you need to know the redox potential. And you need a machine to determine, to estimate, to assess the redox potential of a couple oxidized form and reduced form. And the machine was discovered by Herovsky from Czechoslovakia then in 1959. And then how the electron transfer takes place from one place to another. There could be two, if the distance is not very far off, the typical harpoon mechanism in physical chemistry, electron can start from one place, it is not very far off, it goes, and the other one grabs the electron. So one is losing the electron, other one is grabbing the electron. This is called outer sphere electron transfer reaction. But if the distance is a bit far off, then the electron is mediated by some bridge, and that bridging center will help in talking two different metal ions at a distance. So first electron is generated from one center, through bridging atom or group, it goes to the other center. So this is called inner sphere mechanism. As these things are of fundamental understanding, so this was proposed by the Stanford professor Henry Taube, who got Nobel Prize in 1983. Now the question is, electron, how does it go? We know, but what is the rate of the electron transfer? So for that, the physical chemists started thinking, theoreticians, and the Rudy Marcus was the person who was awarded the Nobel Prize for telling how do you predict the rate of an electron transfer reaction? So that is the fundamental thing of redox processes. And then we have catalytic roles in acid-base and other acid-base reactions. Means we had some breakfast and we have eaten something happened. What something happened, we are going to discuss today. So to sum up, the metal ions will help providing the structural role to the proteins and enzyme, metallocontaining, carrying and transporting electrons and oxygen, catalytic roles in oxidation reduction reactions, and catalytic roles in acid-base and other reactions. These are the basic things. Now, I thought of talking about aerobic respiration, our survival, the metabolism, how actually we are eating food, what is going on. And the reverse reaction is called photosynthesis. As it is for the undergraduates, many people may be knowing lot of things. With my limited knowledge, I would like to reach out to those young minds at a fundamental level, molecular level understanding of these processes. So we get a start with this aerobic respiration, that is our survival. So we eat food, and food are nothing but organic products, whether rice or wheat or anything. So organic product proteins, the organic products, and we need oxygen. And that is processed in our body for our survival. And we reduce oxygen to form water. That is and organic products will give rise to carbon dioxide. So we take organic products and oxygen, and we eliminate carbon dioxide and water. But what is eliminated, your waste that way, is the great for the plant kingdom, because for their photosynthesis, they will have to process these molecules to generate their food, and their food is generated because of these things. But you understand, we have studied, I will spend some time on that, oxygen to water. What is that? From our school days, we have been studying O2 plus 4 electron, 4 proton going to 2 water. Potential is 0.82 at pH 7. So plus 0.82 means delta G is negative. That is thermodynamically feasible reaction, oxygen getting reduced to water. However, if you take oxygen, a water, and you generate oxygen, that is not thermodynamically favorable. That you have to provide energy. And who provides energy? The great sun. If sun is not there, switches off, photosynthesis stops, we don't get food, and we will not survive. That's the whole funda between the aerobic respiration and photosynthesis. Now I go back, as oxygen will play a major role, I go to the elementary level of science. Say oxygen molecule, we know 1s orbital, 2s orbital, 2px, 2py, 2pz, so on and so forth. And it has valence electron, oxygen belongs to group 6. So there will be 6 electrons, 2, 3, 4, 5, 6. The 2s orbital 2 and these 4. And similarly, another oxygen atom will be having this. And these orbitals interact. And even in the undergraduates, you know that there will be situation like this from molecular orbital of RS molecule. And there are 2 unpaired spin on the anti-bonding orbital. So if you have more and more electrons in the anti-bonding orbital, that is, there are high energy orbital, so the molecule loses its stability. If the electrons are out of that anti-bonding, the stability increases. As for example, the strongest bond is generated between nitrogen and nitrogen, forming a nitrogen N2. Now the question is, this is very good, but all the organic molecules which we know, they are all diamagnetic. That is, no unpaired spin in it. So organic compounds are diamagnetic, but oxygen molecule, we would like to use it for metabolism, is paramagnetic. So there is a spin restriction. So these molecules are unpaired electron spin, and the organic molecules are having diamagnetic. So you have to do something. So oxygen molecule, if it gets appropriate energies, is shown here, it is going to these 2 unpaired electron in 2 different orbitals, can be in one orbital, one up and one down, which is called a singlet state. And when one up and one up, both are up, it's called triplet state. But it can so happen in the excited state, 2 orbitals separately, one up and one down. So that would also be diamagnetic, but not like this. They are 2 different states, and they are energetically separated like that. So when oxygen is used as an oxidant, oxidizing agent, you know, there must be certain things which will be able to mediate that talking between the organic compounds and oxygen. Oxygen is paramagnetic, it will not do anything to the organic compound. The metal ions come there. So metallo-containing enzymes, many of them, particularly iron, copper, they're the main, which will interact with oxygen and activate oxygen molecule. So in the process of activation, oxygen molecule with 2 unpaired spin, it will lose its individuality. Now it is under the influence of the metal ion. and then they will become diamagnetic, as for example, peroxide. So O2 2- is again singlet state, or oxide O2- water. So O2- oxide is again diamond. So oxide, peroxide, nature likes, but nature does not like those unpaired spin. More than that, I won't say. All these free radical mechanism I'm not getting into. So this is the bottom line of oxygen. Now, what happens in aerobic respiration? So it is a metabolism, our survival, and I told you is the energy is released in the process. So whatever we eat, we have eaten something in the breakfast, so that has gone to our stomach, and then what happened? The big molecule, a carbohydrate molecule, is broken down, hydrolysis reaction, acid-base catalysis to generate the glucose. Or we have eaten some protein, that will be broken down to amino acids. So what happened? Once that happened, the first hydrolysis, but that is not metabolism. Metabolism finally happened when oxidation takes place of the foodstuff. And during oxidation, what happens? Electrons are generated. So if I tell you, actually we eat electrons, I'm not wrong. We really eat electrons, not in terms of your naked electrons, in terms of bonds, chemical bonds. Electrons are hidden there, forming a bond between the two constituting atoms, if it is a diatomic. And then those electrons generated due to oxidation of food is taken up by someone named NAD. I will tell each and everything step by step. A molecule which will be able to grab electron to get a reduced form NADH. So this is the oxidized form, this is the reduced form. And that potential is minus 0.32. So that means our oxidation of food generates electrons in the negative end, and then like an electrical wire, the electron flows all the way to a positive end. And positive end, there is a big enzyme named Cytochrome C Oxidase. And that enzyme actually, iron copper containing protein, multi-component protein actually. And this provides the necessary electrons, started from food to NADH and traveled like this, one after another. A series of proteins are there. What they are doing, one protein here whose redox potential is higher than the previous protein. And the previous protein was higher than the previous. So that means the right side, right protein with more positive potential will be able to oxidize the protein on the negative side. That is the fundamentals of redox chemistry. So the electron generated from food enters here at minus 0.32, travels due to electron transfer reaction, electron transfer proteins to the end positive at plus 0.82, where oxygen gets reduced to water at pH 7. And this process is thermodynamically favorable. Why? Because O2, 4 proton, 4 electron, 2 water is plus 0.82, so delta G is negative. So it's like photosynthesis is just the opposite of it, the reverse reaction. Energy is supplied, I have said. So water gets oxidized during photosynthesis and starts with plus point. It starts with minus 0.32, our survival. And we end up here. And photosynthesis starts with positive and ends up in the reverse direction here. And then the water gets oxidized, generating electrons, and those electrons flow and finally accepted by NADP+. I'll show you the structures. Just oxidizing agent and reducing agent. They get reduced, and this one helps carbon dioxide and water to combine, providing electrons to generate glucose for plant kingdom. So here is iron copper containing multi-component protein, and here you have a manganese containing protein for photosystem 2. So cellular, I have said is already written here. Quickly, I will go scan through. Cellular respiration is a process that describes the metabolic reactions and processes that take place in a cell to obtain chemical energy. From fuel molecules, food energy is released by the oxidation of fuel molecules and is stored as high energy carriers called adenosine triphosphate. I'll show you each and everything. So electrons generated is stored in terms of energy in the form of a molecule named ATP. So fuel molecules, food commonly used by cells in respiration include glucose, amino acids, and fatty acids. And a common oxidizing agent is electron acceptor, is molecular oxygen. So that's why I showed to you the molecular oxygen is paramagnetic. That is a very, very important issue. All the actions are going on because of tungsten metal ion. Organisms that use oxygen as a fuel, final electron acceptor in respiration are called aerobic, while those do not refer to as anaerobic organism. The energy released in respiration is used to synthesize molecules that act as a chemical storage, is already said. Now, some basic concepts. The knowledgeable ones, you can close your eyes, but for the students, I'll show you there are certain basic conception problems. If I ask a student, I remember my teaching at IIT Kanpur, came 101 L7 with 400 bright students of this country, and you write oxygen plus 4 proton, 4 electron going to water plus 0.82 volt versus NaHe, and ask the student, what is the potential for water oxidation? And I could see that 95 or 90% students said minus 0.82, totally wrong. And I could see a student did not raise his hand, and he was sitting there. And I asked him, what's your name? I still remember his name was Vishal Saxena. And I asked him, what is your All India rank? He says 1. So the JE1, he did not make a mistake. He said, whether you go this way or that way, potential is not going to change. Free energy is going to change. So that's why quickly I'll scan through. Let us consider an equilibrium reaction like this. Equilibrium constant will be like that, all of us we know. For a redox reaction, it will take a shape like this. Oxidized species take electron. Always remember that. And that's why it is called reduction potential. In terms of free energy and equilibrium constant, you can write like that. And then you plug in delta G minus NFE, and you have an expression like this. And this is well-known Nernst equation. But it tells a lot of things. You know, always write like this. Oxidize, electron reduce, and this is the final expression. Now, what happens to the next? Example on redox reaction. You have permanganate, electron, proton, manganese 2, water, potential is 1.5 volt versus normal hydrogen electron, acidic condition. Take iron, is potential 0.77. And in our school days, I remember the titration of iron against permanganate or iron 2+ against dichromate ion. Dichromate, this value is 1.3, and similar reactions. Now what happened? Higher the value of E0, so this guy is higher than that one. Oxidized form of the redox partners, that is, partners are what? Oxidized, and this is reduced. So oxidized form of the redox partner is the stronger oxidizing agent. In the cited example, 1 equivalent of permanganate, because it gives 5 electrons, will oxidize 5 equivalent of iron because it requires only 1 electron. So 1 event will take care of 5 of them. Will oxidize. Remember, always oxidized form or reduced form. What we have learned? That more positive one, as I said, the electron transport chain in protein and enzyme, more higher value will be able to oxidize the one protein which has less positive value. Now, what is stability field of water? We have water, that is fair enough. What is stability field of water? Let us consider how the potential oxidation reduction of water changes as a function of pH. So this is the reaction I'm talking about, and this is the value. And then you write what I've said to showed you just now. You write like this. The E is a working potential. You can change it, but you cannot change that. It's standard value. Now you have acidic condition. So proton 1 molar, you plug in for 4 electron. So you will take a shape like this. Then if you take pH 7, which is proton concentration minus 7 molar, then what will happen? This value, what you had, this, the fundamental acidic condition value 1.23 minus 0.59 into the pH. So your value is 0.8. What you have learned, whatever is the value in the acidic condition, when you had gone to neutral, the potential positive value has decreased. If we go further, if we increase the pH, this potential will go down. And the take-home message is, you remember 0.06 and 7. So 0.42 will change. So from here, 0.42, from here, 0.42. Now what is important here, oxidation of water at pH 7, that is your nature, value is 0.82 volt. So if, and then I'll show you the next one. Now you take the reduction of water. This is the without equated form, 0.0 by definition. And you write the same expression and you get the same value. Because here it's 2, so it will cancel out. And the proton is also 2, so you will be having that. Now pH 7 minus 0.4. So these value is important. So biology is telling us the previous value of plus 0.82 is the limit at pH 7 for the oxidation of water and for the reduction of water minus 0.42. And if you increase the pH, the value will keep on decreasing like the previous one. So this message is most important. Water is stable at pH 7 in the potential range minus 0.422 plus 0.82 NaHe. This is called the stability field of water. What is the take-home message? There cannot be any protein or enzyme doing the job of redox reaction whose value is more than 0.82 or less than minus 0.42. What would happen? From our body, the skin will bulge out, oxygen will come out, or hydrogen will come out. That does not happen. So all the proteins and enzymes, they are potentials, redox proteins, their potential are constrained to lie within this limit. That is the funda of the redox chemistry. Now I showed you that the reducing agent is NAD plus. Our oxidation of food generates that. That is fair enough. So NADH, this is oxidized form. So it takes up 1 electron, 2 electron, and 1 proton and generates the reduced form. So this is the oxidized form like this, and reduced form is the plus charge will not be there, so that is the reduced. And similarly, if you have instead of OH one phosphate group, that is called NADP, which is present in photosynthesis. Otherwise, the whole thing is same. So in photosynthesis, that is called NADPH and NADP, and in respiration, we call it NADH and NAD+. That is the difference because of additional phosphate. The potential we know minus 0.32. Now there are 2 molecules. It's called adenosine diphosphate and adenosine triphosphate. Remember only the simple thing. That's what I try to enjoy doing science. So when you say diphosphate, this is full level understanding. So diphosphate means 1 phosphate, 1 phosphate. So there is a TOP bond 1. Di will give only 1. If it is a triphosphate, so it will give rise to 1 phosphate, 1 phosphate, 1 phosphate. So number of POP will be 2. More and more this anhydride compound, ATP, than ADP. More and more generation of anhydride, like your acetic acid and acetic anhydride. Acetic anhydride is more powerful. Same here. ATP, this molecule is generated, and to generate this one from ADP and inorganic phosphate, you have to pump energy. So ATP is a nucleotide. These things are written there. So ester of pyrophosphoric acid, nucleotide is adenine, this thing, and this is called pentose sugar ribose, and this is phosphate. And same here, only difference is 1 bond, and that is 2 bond, ATP, ADP. ATP is very, very important. This is a molecular currency of intercellular energy. So we have money, and in biology that money is ATP. In this role of ATP transports chemical energy within cells for metabolism. So electrons are generated and it is stored in terms of energy. And you need an enzyme to process this ADP, diphosphate and inorganic phosphate to do this. The name of that enzyme is ATP synthase. And ATP synthase is general term for an enzyme that synthesizes this ATP from ADP and inorganic phosphate. That is the way. And these enzymes are of crucial importance in almost all organisms because ATP is the common energy currency of cells. So ATP synthesis is important. Synthase generates ATP from adenosine diphosphate and inorganic phosphate. So ADP is there, plug it in, you form ATP. More and more ATP means more and more anhydride bond means more and more energy. I am talking right now, so my reaction is going on reverse. So my ATP, which I store during my sleep at night, I am generating more and more ADP and inorganic phosphate, I will feel tired. And you are listening to me, you are not making much movement of your, arms or thinking. Your thinking is on, definitely, but the movement is not there. So mechanical motion is not there. So your ATP is not getting exhausted that much. What is happening with me? Now, aerobic metabolism, aerobic respiration or metabolism. As I said many times, oxidation of food generates electrons. And this is happened, and Cytochrome C Oxidase, whatever I have said so far, again pictorially presented. Now let us take the stages in the, the extraction of energy from foodstuff. So you have a fats. So what happens with fats? So we have eaten fat, we generate fatty acids and glycerol. We have eaten some bread, some idli, some or dosa or some bread. So you generate basically glucose and other sugars. We have eaten some egg or something during breakfast. So we generate amino acids. So this is what we eat, and this is what after hydrolysis this happens. But there is a complex mechanism. I will not bother the students, undergraduate students, but there are a complex mechanism by which these compounds, whatever we have, oxidation you follow, there is no problem. So these molecules, and these molecules will get oxidized during metabolism and generate electron. And those electrons are these electrons for processing oxygen going to water. And this reaction is called oxidative phosphorylation. So oxidation is going on, and phosphorylation means ADP to ATP. That's why the name is. The glucose gets burnt out, carbon dioxide energy is released. But in the formation of ADP to ATP and water that is happening with me is minus delta G. But for the formation, delta G is positive. And whenever this reaction takes place, our movement and everything, I made a mistake. This arrow should be here. So these and ADP, phosphate and proton, arrow should be here. And we generate carbon dioxide and a lot of ATP we generate. And ATP we are generating because we are eating food, and food is getting first hydrolyzed to smaller molecule, then getting oxidized through oxidative phosphorylation, generating more and more of ATP molecules. A resting human consumes about 40 kilograms of ATP in 24 hours. So continuously, we are doing something, and whenever we are taking a rest, ATP is being stored, and whatever we are doing, ATP is being exhausted. So we are consuming so much of ATP. Oxidative phosphorylation is the terminal process of cellular respiration. I have said in eukaryotes, the cell, during oxidative phosphorylation, electrons are transferred from NADH or FADH2 created in glycolysis, fatty acid metabolism in the Crepe cycle to molecular oxygen via a series of protein complexes located in the inner mitochondrial membrane. Mitochondrial is the reaction flask where redox chemistry is going on. And this is the way things are happening. ATP synthesis, I have already explained. This is the cartoon. It's a complex thing, but very simple actually. Aerobic metabolism. So whatever you are eating, carbohydrates, protein, the glycolysis is going on. And all these fats are doing beta oxidation, eventually pumping electron to certain things called acetyl coenzyme, and it is called Crepe cycle or citric acid cycle. Don't get into all these complicated names, but what is happening? The electrons generated through this cyclic process, and electrons are generated to NADH. And once NADH gets an electron transport chain, oxygen gets to water, and adenosine diphosphate, inorganic phosphate goes to ATP. So there are three stages. One is preparation for entry into Crepe cycle. You have to have food, and food should get oxidized, metabolism. And first phase of metabolism will enter to the Crepe cycle. The removal of energized electrons. So removal of the energized electrons. Why energized? They were in the terms of food getting oxidized, those electrons. And finally, those electrons are pushing here. ATP synthesis going on, and which is oxidative phosphorylation reaction. So here is the food, here is the processing through electron transport chain. I showed a lot of arrows, and that's what happens. Now, this is another cartoon. I said acetyl coenzyme, Crepe Cycle, and you see many ATP and the inner compartment, outer compartment, electron transport chain. And we have said NADH will give electron here, and finally the electron will go to Cytochrome C Oxidase, which will process oxygen to form water. More and more water is formed with the help of proton in the system. Proton is a must for the functioning of that. And you have to also understand scientifically that electron, when you add, the negative charge increases. So there must be addition of proton to reduce the negative charge. So any multi-electron transfer reactions, nitrogen to ammonia, is a 6-electron process. Oxygen to water, 4 electron. And you see O2, 4 electron, 4 proton. N2, 6 electron, 6 proton to 2 ammonia. Whenever you have number of electrons more, it is always associated with number of protons to counterbalance the Coulomb attraction or the charge issues. And this actually for the completion I wrote, what is the acetyl CoA does? No, actually don't, it is not that important. It is basically helping to go to complete the pyruvic, your Crepe cycle, which is the metabolism and the biochemistry thing. So it is the cartoon is more important. So glycogen to glucose, fats, glycerol, pyruvate, I wrote here certain names. So they are processing and finally entering to Crepe cycle. And that is important. And those electrons from the food, they are processed through this channel complex mechanism, and electrons enter into the electron transport chain. It starts at the minus 0.3 to end and ends at the plus 0.8 to end. Cytochrome C oxidase will take care of it. So Crepe cycle, this is the main thing. A series of chemical reactions that occur in most aerobic organisms and are part of the process of aerobic cell metabolism, by which glucose and other molecules are broken down in the presence of oxygen into carbon dioxide and water to release chemical energy in the form of ATP. That's what happened in this thing. Now you can see acetyl CoA structure. I will skip it. Now what you have to do, so you have to process this oxygen to water. So you need 4 electrons to be transferred, and 4 electrons to be transferred. There is an enzyme name I wrote, Cytochrome C Oxidase. The complex protein is a multi-component. So one component like this. Let us see one iron is there. So iron will be at one instance iron 3, another instance iron 2, electron transfer protein. That means electron will be available with this protein, heme A, and when necessary, it will release. That's the fundamental thing. This is a copper 2 and copper 1 bridged another protein component. So copper 2, copper 1 means copper 1 will also become copper 2. So it will also release electron. So these are basically giving electron, because you have to provide 4 electrons, not just coming like this. The electrons are stored in particular electron transfer proteins, and then the electrons are released. And there is another component where both iron and copper are present. Both. This is the complex. Forget about it. The first one, iron containing, will give electron. Dicopper containing will give electron. Stored electron. And then it will go to this center, the main center, where iron and copper will process oxygen to water. This is a complex mechanism. I don't want these school kids to get into this trouble. So iron 2 with a porphyrin and histidine, 2 state, that means one side is vacant. And then you have iron and copper 1 and iron 2. So iron 2, oxygen, copper 1. And then what happens? First, it reacts with iron due to redox potential. Potential of iron 3,2 will always be more negative than that of copper 2,1. So it will react with this first to generate that, and then it will react with copper. Eventually, one electron is transferred from here, another electron is transferred from here, and you have a peroxide. And this peroxide is from this complex thing, and eventually you will be having the generation of water formation will be there, and the cycle repeats. So water formation is basically reduction of oxygen takes place with the iron copper containing complex protein named Cytochrome C Oxidase. That is not very important at this point. The important point is how the iron and copper got electron. They got electron from this center, from that center, and those electrons are added. You will find time to time some electrons are coming. Those are the centers. They were in the oxidized, reduced form, so they will get oxidized and pump electron. Another reduced form will pump electron. That is the way it functions. So this is the complex mechanism, but the simple way I would say, we eat food, food gets processed, and food gets oxidized, electrons are generated, and then those electrons are utilized for oxygen reduction, oxygen to water, and it's an exothermic reaction. Because of that energy availability, the reaction between oxygen and proton and water takes place, and you have the formation of ATP in your body or our body. So ATP synthesis, if you require, that means you must have the situation like this of complex thing. Now, I switch the gear. This is even more interesting part. The aerobic respiration, I have said, negative end to the positive end. Iron copper containing multi-component protein, I have already said. One is iron copper, one is simple iron, another is copper copper. So all these things are in one enzyme. The structure was known in 2000. It's a very, very important thing. Photosynthesis is reverse. So you have certain things like this. What is happening here? You have a chlorophyll. You can see I have shown the structure. This is a huge tail. What is the need of that? If the molecule chlorophyll, which is on the leaves, if they are water soluble, so whenever there is a rain, then what we will see, all green pigment is getting washed away and the plant is no more green. So the pigment is formed in such a way, this group is called phytyl group, and this hydrophobic group does not make this molecule to get soluble in water. So you see all over the place, the groups are such that will make this porphyrin, special porphyrin, unlike our hemoglobin, this porphyrin, chlorophyll porphyrin, but the same for nitrogen pyrrole and water insoluble. And they are green in color. Magnesium is present, which we have learned in our school days, and they are beautiful colors are there. One is around, say, 450 kind of, another is around 680 kind of. So these are the things which will pay much attention in our discussion today. One will be at close to 700, another is less than that. What are the steps involved in photosynthesis? So, light collection. So that means light is required because of sunlight. Light collection via chlorophyll and chlorophyll-like molecules, pigments, and conveying the energy to a center. That center is a head office where all chemical reaction will take place. Mitochondria, reaction center. The oxidation of water to dioxygen and the reduction of NADP plus to NADPH. I told you there will be one phosphate group, unlike our aerobic metabolism. That takes place. So NADP plus water will get oxidized, that means gives electron, and eventually will form NADPH. And in the process, what happened? ATP is also formed. So that means energy you are supplying, so ATP will be formed here as a byproduct. And the last step is NADPH, the absorption of CO2, oxidation of this guy, NADPH, reduced species, and formation of plant glucose, abbreviated as CH2O. So C6H12O6, so CH2O the component. And this reaction goes on. So now the bottom line is what? The most important thing is water has to get oxidized to generate electron. This water is getting oxygen, in the process getting electron. And those electrons are pumped to do NADP plus, and NADP plus is getting reduced to NADPH. More and more NADPH is formed. They will be able to process carbon dioxide to generate glucose, the food for the plant kingdom. So food will be generated. This is available. We have already released carbon dioxide, but NADPH has to be formed. And NADPH will be formed when water gets oxidized. So if water does not get oxidized, if there is no rain, if we don't water our plants, they will die. That's the basic fundament. And you see there are something light event. to simplify it like this. This is a complex, some enzyme, and let us call that enzyme is a S0 state. It's basically photochemistry. So 1 is 0 state, the 1 state, 2 state, 3 state, 4 state. So there are a bunch of 5 states. This was done from Berkeley. So these are 5 states, that is fine. What is the difference between these states? This is the reduced form, and then one light falls on it with a pigment called P680. That pigment will get oxidized, and in the process, S0 will become S1. That is more oxidizing. So this is reducing, so slightly oxidizing. Another light, another oxidizing, another light, another oxidizing, another light, another oxidizing. And when S4 is formed, then when S4 is formed, then absolutely no issue. This S4 can process water oxidation to generate water. But to cut a long story short, complicated one, S0, S1, S2, S3, S4, these are all photo states, photoexcited states. So S0 is the bottom line, then higher energy S1, higher energy S2, higher energy S3, and finally higher energy S4. And light event, how many? 4 light events. And there is a pigment 680. So that means this pigment absorbs light at 680 nanometer. That is the meaning. And during these 4 light flashes, this reduced form of the manganese cluster will become highly oxidized form. And when they are highly oxidized, they are capable of oxidizing water to grab electron so that they go back to this place. That is the funda. But this reaction is not so simple. So I wrote like this. Upon photo excitation of P680, photo excitation, a series of electron transfer reactions between cofactors within the protein take place, series of electron transfer reactions. Then there is certain things when this P680 generates P680 plus. The P680 plus should come back again. Otherwise, one light event and will stop the photosynthesis. That cannot do because it should cycle through. So P680 will lose P680 plus, but then P680 plus also should come back. And that I will explain right away. And there is a component of manganese cluster. Now you see certain small thing. There is certain component we have studied in our BSc days. Quinone is oxidized form. Hydroquinone is a reduced form. So hydroquinone, you oxidize, you form quinone. So quinone hydroquinone couple, which is called ubiquinone in nature, also takes part as a redox partner, redox reagent. And also there is a protein named plastocyanine. In spinach, you have it. And we have in our body also copper with 4 groups. What kind of group? Histidine, and then methionine and cysteine sulfur. Cysteine sulfur means SH, deprotonated, coordinated, and thioether sulfur. Written strongly distorted geometry. So copper 2 would prefer square base geometry due to Jahn-Teller distortion. So copper 2 is not ideal. It is a distorted geometry, and copper 2, because of D9 electronic configuration, not D8, D9. So you have strongly distorted coordination sphere of a protein named plastocyanine, 3 plus 1. So 3 plus 1 comprises 2 histidine, 1 methionine, and 1 cysteine. What it does? Electron transfer. So in one instance, it will be copper 2. Another instance, it will be copper 1. So copper 2, copper 1, copper 2, copper 1. Like permanganate, manganese 2, permanganate, manganese 2. Iron 2, iron 3, same process. Similarly here, quinone, hydroquinone, quinone, hydroquinone. It is a redox reaction, and copper 2, copper 1 is the redox reaction. There are certain things called iron sulfur protein. So this is the structure. Iron sulfide, S2 minus, and these are cysteine sulfur in protein. What they do? Iron 3, I have written iron 3. Sulfide, so I sulfide 2 of them. And cysteine sulfur means S minus, SH. S minus, S minus, S minus, so 4. So it will have a charge of 2 minus. So its 3,3 protein will go to 3,2 protein after taking electron. So the charge will be 2 minus, 3 minus. So this is present plant pyridoxine. That means photosynthesis, you need that kind of, or even in our body, we need this plant pyridoxine. So basically, it's a protein with this coordination, 4 coordination, 2 sulfide and 2 cysteine sulfur from protein, and from protein 2 cysteine sulfur, 2 sulfide. 3,3 will become 3,2, or 3,2 will become 3,3. 3,3, 3,2, 3,3, 2, 3,2 means electron transfer going on. At one instance, they will be 3,2, another instance will be 3,3 and release the electron. That's the whole funda. And there is something called Z scheme. Why is Z? This, and then this. So this is Z. Now what is happening is the redox potential scale. And we have already learned water oxidation takes place as plus 0.82 NiHe. And there is a manganese cluster which helps in oxidizing water. And what is the chemical process? There is a pigment called P680, light falls on it, and it goes to the higher energy. And it goes to the excited state and loses electron. But electron cannot just go away. That electron will be taken up by quinone. And what is quinone we are talking about? We are talking about this kind of quinone. So quinone fellow oxidize, will take electron, will go back here. So the P680 will become P680 plus star, then plus excited state, high energy, then lose electron. And that electron is taken up, quinone, and quinone fellow will give electron eventually to something called plastocyanine. What is plastocyanine? Plastocyanine is this guy, is a copper 2 after getting electron, copper 1. When you need electron, it will become copper 2, losing electron. So if the center will become 2 and 1, 2 and 1 will go on. So that electron generated from this P680 high energy, that electron first goes to quinone, then goes to plastocyanine. So if I ask you the question, the electron generated from this pigment, where it is now? It is with plastocyanine. So plastocyanine in which form? Copper 1 form. Because copper 2 has got an electron, becoming copper 1. And this process, this portion from here to there, this is called photosystem 2 process, photosystem 2, where water oxidation takes place. And another thing is called photosystem 1. What is that? There is another pigment, slightly different. It absorbs at 570, and it is P680. So 680 it absorbs, P70 it absorbs. And then it goes here. And once it goes there, high energy state, it will also lose electron. And those electrons will be taken up by pyridoxine. What is pyridoxine? This fellow. So 3,3 fellow, 3,3 will become 1,3 and 1,2. So that is a redox process like permanganate, manganese 2, iron 3, iron 2, exactly like that. Now this process is called photosystem 1. And from here, the electrons will go to form NADP plus with proton, and the electrons which have come to become NADPH. That is the funda. Now the question is, how P680 plus after losing electron gets back, we have to understand, and how P700 becomes P700 plus after losing electron. How does it go back for the second event? How does it go back for the second event? That we have to understand. So electron transfer step. These are all elementary redox chemistry. Step 1, P680 goes here, loses electron. P680 light plus electron. Endothermic reaction. Why endothermic? You have to give energy, otherwise it will not happen. And then the electron released will be taken up by quinone, which was present in the oxidized form, will now become a reduced form. So the quinone fellow, I have already said, it will be in the reduced form now. So that is there. Now this P680, which is formed, how it will go back? It will go back interacting with some tyrosine. I will come to that point soon. And this tyrosine, one amino acid, so this tyrosine gets oxidized to form a radical, and oxidized means the electron is lost. So that electron is taken up this P680 plus to become P680. So we know P680 plus can go back. But we have to understand how to get back this tyrosyl radical fellow back to tyrosine. That is what done by this manganese cluster fellow. What it does, see, manganese cluster fellow in the reduced form, that means lower oxidation state, and they react with this tyrosine radical and tyrosyl radical. So this reduced form of this cluster becomes oxidized form, and electron lost is taken up by radical to go back to tyrosine for the second event to take place. And in the process, this oxidized form of the cluster actually oxidizes water to generate proton, oxygen, and of course, electron. And so now the question is, we have learned how P680 plus can go back. P680 plus goes back to P680, reacting with tyrosine. The tyrosyl radical is generated, but it is back. Then we have to understand radical, how does it go back to tyrosine? The radical fellow reacts with manganese cluster reduced to become oxidized, and tyrosyl radical goes to tyrosine. There is no problem. So that will take care of it. But we have to understand the electrons generated from this water oxidation, they are associated with whom? With plastocyanine, which I have shown already. The electron generated all the way, they are all with plastocyanine. The plastocyanine has the electron. So plus overall reaction is what? Plastocyanine, which is in the oxidized form, that means copper 2 form, is reacting with the reduced form of quinone to generate quinone oxidized for the second event, to go back here for the second event, and plastocyanine oxidized to go back to the reduced form. Means electrons are with plastocyanine. This is photosystem 2 steps. And the third step is what? Third step is, so electrons are with PC, that means copper, protein, your, what do you call, plastocyanine, copper 1 state. Now P700 becomes P700 plus. So how P700 function? So P700 plus generating electron. So P700 form and the PC in the reduced form plastocyanine will go back to oxidize, releasing electron, and that electron is taken up by this guy to go back to P700 for the second event to take place. So again, the second event will take place like this. Now the electron is gone. This electron we have not consumed. We have only thought P700 plus, and already electrons are with the plastocyanine like this in the copper 1 state, reduced form, and they are doing this. But this, what happens to that electron? That electron is taken up by pyridoxine in the last step. Last step means 1, 2, 3, 4. So first step 1, step 2, step 3, and step 4. So step 4, what happened? This electron from P700 takes up by pyridoxine oxidized form, becomes reduced form, and delta G becomes negative because thermodynamically feasible. And here iron 3,3 become iron 3,2, that happens. So overall reaction is what? Plastocyanine in the reduced form, as if it is reacting with redoxine in the oxidized form and generating that. Actually, it is not happening. You need those light, otherwise it won't take place. And these two processes, that means this one and that, this process is going on in photosystem 1, and this and that is going on in photosystem 2. So the cooperation between photosystem 1 and photosystem 2 creates an electron flow from water to NAD+. This pathway is called the Z scheme. Why? Because the redox diagram from P68 to P700 resembles the letter Z. And this is the excess structure of photosystem 2 published in 2004 in Science. Now you see there is a cluster here. Forget about all complexity. I will make the life simple. You have this turquoise color 1, 2, 3. So one manganese, another manganese, and little bit away another manganese. So this is a cube. This is a cube, and this is another cube in the bottom. Oxide, manganese, manganese. Manganese, calcium, oxide. How many manganese? 4 manganese. We have only 2 and 3, but there is another one. So it is written manganese 3 calcium. So manganese, 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 calcium. 3 plus manganese is this manganese. So this is the structure. People took, 100 years to understand the excess structure of photosystem 2, the manganese cluster. But you see in this structure, there is a nearby tyrosine. And I told you the tyrosyl radical generation is important. So distorted Cuban structure, and that is the place where water gets oxidized to oxygen. But exactly how it happened, water comes, gets bound, all those steps are still unknown. All over the world, the top scientists are working on it to understand the chemistry at a molecular level. So distorted Cuban core, manganese is Ca plus manganese core. And when you have manganese 4, all this highly oxidized form, that is the form which is the so-called S4 form. And what is S0? The reduced form is S0. And S form is manganese 4 kind of. That means highly oxidizing species. Highly oxidized species. And that one oxidizes electron and gets electron to go back to its reduced form. That's what happens in photosystem 2. So this is the one. Yes.
We have almost reached the time.
Yes, I'll finish in 2 minutes, 1 minute or 2 minutes.
Yeah.
Now,
go ahead, please.
My greetings to all of you, particularly the bright young minds of this country, in the mission of developing quality human resource for the nation. We should be a good human being with a value system targeted to do quality research. Whether it is a teaching or research, do some fundamental understanding and enjoy doing science. That is the message, whatever I tried to say at a very elementary level. And I thank you all for your patience. Thank you very much.
Thank you very much, Professor Mukherjee, for a wonderful talk explaining at the fundamental level what is going on in various biological processes. So now we can actually take up some questions.
Sure. Please.
So the first question is by Susim Sabuj Sarkar. He's asking why oxygen needs to be diamagnetic. Is it because it has to react with a diamagnetic organic molecule?
Exactly. That is the answer. Because oxygen is paramagnetic. So it cannot, because of the spin issue, the spin reorganization issue, when you have a 2 spin up, then you have to force energy. You have to give electron to pair up. And that kinetic barrier is the main problem. So that kinetic barrier is the issue. That's why the molecule and oxygen, they go hand in hand. That means diamagnetic singlet state, and then the reaction takes place. Correct answer.
So, yeah, he continues with another question, that how this magnetic state affects reaction.
Oh, so the point is, if yours, that means oxygen molecule.
Yes.
So if the oxygen molecule is paramagnetic, oxygen is paramagnetic, it will definitely react to the tungsten metal ion. Why? Because if you have a protein, iron containing protein, it has 4 unpaired spin, because iron 2. So iron 2 has 4 unpaired spin in a roughly 6 coordination. So that unpaired spin and oxygen unpaired spin, they can interact and giving rise to a, in magnetic terms, called anti-ferromagnetic coupling. So unpaired spins are quenched by interaction with the oxygen, and in the process, diamagnetic oxygenated, metal coordinated oxygenated species is formed. That is the reaction. And then they are capable of reacting with organic substrates.
Thank you. I think that takes care of the question by Mr. Sushim. The next question is by Venkatesh Jha. He's asking, hydrogen and oxygen making water fuel cell reaction is an extremely vigorous reaction. How are the inner and outer membranes of mitochondria able to bear this, along with tolerating the proton gradient? That is the first part of the question.
So this is a very complex question, I must admit. So the first thing is a membrane reaction, because electron and proton, if they combine, then they become hydrogen atom transfer reaction. So nature has designed a membrane, the Cytochrome C Oxidase kind of membrane. One side, proton moves and another side, electron moves. They do not get combined. But in the other situation, in the fuel cell and all those, that membrane issue is not there. So they will combine H plus and electron. But in nature, very, very slow release, proton gradient is generated, and then electron and proton will never be able to combine. But when necessary, then only proton and electron through those membranes will be able to interact and complete the chemical reaction. Because whenever you have a multiple electron transfer, then electron and proton has to be there to balance the charge and Coulombic attraction and repulsion. And in all cases, like in photosynthesis, you have also 4 electron problem. So there is a membrane called thylakoid membrane in plant kingdom. So that membrane separates out electron and proton. Like in photochemistry, we learn one thing, that how to stop the back reaction. That is, a donor is excited, then you generate an electron. If they recombine, then your energy is lost. So recombination process of a hole and electron should be eliminated. And that's what nature does using the membrane they have.
Okay. He has another question, that how far are we from employing these biopolymers, mitochondrial walls, in man-made machines like rocket propulsion systems?
Actually, I really cannot answer. It is a very, very complex issue. Fundamentally, understanding-wise, it is really challenging one. But even to whatever I have said so far, to get to this level, it has taken about 100 years at a molecular level. And I hope this question is fantastic one day, that this energy, what we understand, we'll be able to utilize it in an appropriate form to use it for our industrial processes, including the rocket fuel and things like that. I hope, I'm sure one day it will happen. It is a matter of time. Human being minds, they are wild minds. They're actually restless. Always you try to think something, to come up with an idea. A few years back, we did not know a lot of things. But nowadays, we have been able to understand how these reactions take place. As I said to you, our survival is Cytochrome C Oxidase. And the excess structure is reported only in 2000 kind of situation, Photosystem 2. Only recently we know the excess structure. Even knowing the excess structure, we do not know how one oxygen molecule comes and how it gets first electron, second electron, third electron, fourth electron, and becomes water. Still that is not known. Because the system is so complex. So what the scientists try to do, bioorganic chemists, bioinorganic chemists, biophysical chemists, that means basic inorganic, physical, and organic chemists with biology inclination, they try to model one reaction. That means a small reaction you understand, then you know multiple what happens. That is the way science, in my opinion, develops. I hope that is a fantastic question, and one day maybe we look forward to having the answer of that.
So to your earlier explanation, Venkatesh also asked that does that mean that the reaction that you were talking about is carried out slowly to minimize vigorosity?
I think so, because the controlled manner is important. If the reactions are takes place in a controlled manner, and that is basically that the immediate mixing, slow process, redetermining step will be slow. That way, I think other side reactions won't take place and everything will remain intact. And whatever reaction we wanted to get, and nature designed in such a way, you get the product. I'm sure these kinetics will play a major role in the, the conformation of protein, their positioning, and the interaction with the substrate. All these things are very, very delicate issues. That is a very important question.
Thanks. Are there any other questions from the audience?
Can I ask directly?
Yeah.
Please go ahead.
Okay, so sir, can you tell this thing that what you told about the 0.8 the redox potential thing? Why it will not be reversed? That I think got confused. That redox potential thing.
Try to understand. Generally, in the majority of textbooks, that it is said O2 plus 4 electron plus 4 proton going to 2 water, E0 value is 0.82 volt. It is no problem. Oxygen gets reduced to water at a potential 0.82 volt. But the misconception, what happens in the textbooks, that is when you ask this question, water oxidation, then the student always answers minus 0.8. It's a wrong concept. Potential will never change. Potential is an intensive property. It is the free energy which changes. When oxygen gets electron to go to water, it is exothermic. But when water gets oxidized, it is the endothermic. That means delta G will be positive for the reverse reaction. Potential won't change. Because delta G NFE by definition is oxidized species taking electron going to reduced species. That is the way definition. So what happens? The potential of one side or the other side, it will remain the same. That is the message I wanted to say. For any system.
So sir, if potential would not change, so that means that the reverse process will be easy, then because the potential is the positive in reverse process also.
Potential does not, redox potential I'm saying, a reaction is driven by free energy. So delta G is equal to minus NFE. When the definition is oxidized, taking electron, going to water. That is the definition. So delta G is negative for oxygen getting reduced. But water getting oxidized, potential remains fast, same. But the direction is different. So delta G has to be now positive. That's what I say. The definition is left to right is a negative potential, free energy. But when you write the reverse way, the potential does not change. Free energy of the process changes. That means one exothermic reaction is become endothermic. Why endothermic? If water oxidation is so easy, we don't need sun. Why do you need sun? We need sun to make the endothermic reaction to proceed. If sunlight is not there, then water will never get oxidized. And for us, oxygen going to water, we can do it. Or that we don't need any sun. If somebody gives us food, our body will be able to prepare water. But for the plant kingdom, water to oxygen, because they don't need oxygen, oxygen is their byproduct. They need actually electron to process carbon dioxide to get to the glucose for the plant kingdom. That is what I wanted to say.
Okay, sir. Thank you for the clarification. Sir, I have also one more question.
Yes.
The last question. That is that, can you tell me this, that outer sphere process and inner sphere process, that thing I did not understand what you told.
The point is, this is basically the standard electron transfer reaction. You just see there is one component and the other component. In a reaction vessel, when we do the titration, so we have in a conical flask, say iron 2 solution, condition is acidic and all those, and in a burette, we have the dichromate or permanganate, whatever. So they come, they interact, and immediately there is a reaction. So this oxidizing agent is coming, and iron is already present, and they react immediately to go to iron 3, and dichromate becomes chromium 3, permanganate becomes manganese 2. This immediate reaction is called, in a typical, harpoon mechanism. That means they are coming closer, one losing, one accepting. Donor acceptor kind of. One losing, one taking. But if the distance is far off, then this electron cannot go, and it has been estimated by many studies. If the two component is more than 20 angstrom away, then the electron cannot move there directly. So you need a mediator. So this one is the two component. A mediator is an organic kind of compound bridge. So electron lost goes there, and that electron is passed on. When there is an involvement of a bridging atom, so that means bond reorganization takes place. So that is called inner sphere electron transfer mechanism. And when two components are there, no change in coordination geometry. Coordination geometry remains the same, only charge changes. So that means oxidized form, so smaller size because more attraction, and reduced form, repulsion, oxidation, repulsion. But bonds remain the same. And that is called outer sphere electron transfer. All these proteins, they are all outer sphere electron transfer. But when a protein interacts with oxygen, like hemoglobin, that is an inner sphere mechanism. Because coordination geometry of hemoglobin or myoglobin in the deoxy form and in the oxy form is getting changed. That means coordination geometry changes in inner sphere, coordination geometry does not change in outer sphere during the electron transfer process.
Okay, sir. Can you recommend some books or something that where we find this inner sphere, outer sphere, this thing more clear?
Actually, it sounds very funny. Actually, I have been requested to write a book for the last 2 years. Now the book writing is almost done. So I know maybe 1.5 months, it will come to the world scientific publisher will publishing inorganic chemistry, structure and principles and reactivity. That I am going to write, whatever I feel like. There will be a lot of physical chemistry component, organic, bio, in inorganic chemistry. But from available books which are present already, you can study Atkins, Shriver, and Langford book. Atkins, Shriver, and Langford book, inorganic chemistry. Atkins is physical chemist Atkins. Atkins, Shriver, and Langford, and go to the redox chemistry chapter, inner sphere, outer sphere. It is written properly.
Thank you, sir.
Thank you very much.
Okay, I think, yeah, thanks a lot. Because of the time constraint, maybe we can, we will not take questions anymore. I'm sure that the younger students, they can contact or write Professor Mukherjee, and he would be more than happy to help them in whichever way it is possible. So with this, let me thank Professor Mukherjee once again. As I understand, several of your PhD students and postdoc, they are faculty members in various eminent institutions. They will also continue to support resonance and science teaching in general. Thank you.
All the best.
So with this, we stop here, and the next session starts at 11:30.
Thank you, Professor Mukherjee.
Thank you very much. Bye-bye.
Bye.
Bye.
So we take a short break.
Yeah, we take a short break and come back at 11:30 with the next talk.
Yeah.
Thanks, everyone.